Hello, welcome to 4.2, area. So, sigma notation, the sum of the terms A1, A2, A3 through A sum n is written as sum I goes from 1 to n of AI, which is A1 plus A2 all the way through to A sub n, where I is the index of summation, A sub I is the ith term, so that's the ith term of summation of the sum, and the upper and lower bounds of summation are n and 1, so it goes from 1 to n. Note the upper and lower bounds must be constant with respect to the index of summation. So you couldn't say it goes from I to 2i, that wouldn't make sense. However, the lower bound doesn't have to be 1. Any integer less than or equal to the upper bound is legitimate. So for example 1 says the sum as I goes from 1 to 7 of I would be what? That would just be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, and that's going to work out to be 28. The sum as I goes from 0 to 6 of I is going to be 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6, and that's 22. I get 21. Yeah, 21, not 22. Okay. How about j goes from 1 to 5 of j squared? That's 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And that's going to be 1 plus 4 plus 9 plus 16 plus 25, and we get 55. How about k goes from 1 to n of 1 over n, k squared plus 1. That's 1 over n times 1 squared plus 1 plus 1 over n times 2 squared plus 1 plus 1 over n times 3 squared plus 1 all the way up to plus 1 plus n squared plus 1 over n times n squared plus 1. And we can't really simplify that because these first several we could, but it goes up to a certain value, so we kind of just leave it like that pattern, showing the patterns going on. And the sum I goes from 1 to n of f of xi delta x, that's f of x1 delta x, plus f of x2 delta x, plus f of x3 delta x, plus f of xn delta x. So the dot 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 means all the terms in between, because it's not possible to list them all because there's not a defined value. Now note that the sum I goes from 1 to n of ki, a sub I, you can pull that k out. It's just a constant. It's not affected by the I, so you can pull it out and sum those up. And the sum as I goes from 1 to n of a sub I plus or minus b sub I will be the sum I goes from 1 to n of a sub I plus or minus the sum I goes from 1 to n of b sub I. So you can split them up into their own summation symbols. So let's look up some summation formulas, what they add up to. Now if you ever do the sum I goes from 1 to n of c, that's just c times n, because you're doing c plus c plus c n times. The sum I goes from 1 to n of I, that's going to be 1 plus 2 plus 3 all the way up to n, is n times n plus 1 over 2. The sum I goes from 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. And the sum I goes from 1 to n of I cubed, that's 1 cubed plus 2 cubed plus 3 cubed and so on, is n squared plus, or times n plus 1 squared over 4. So evaluate the sum. We have the sum I goes from 1 to 20 of 1 minus I minus 1 squared. We're looking here is 0 squared. So 1 minus 1 is 0. Plus 1 squared plus 2 squared plus 3 squared plus 20 minus 1 is 19. Plus 19 squared. So this will become 19, I'm following this formula, times 19 plus 1 times 2 times 19 plus 1 all over 6. That's 19 plus or times 20 times 39 all divided by 6, which is 2470. And the sum of I going from 1 to 10 of I squared minus 1, that's the sum of I goes from 1 to 10 of I squared minus the sum I goes from 1 to 10 of 1. So for the first one, we're going up to 10, so that's going to be 10 times 10 plus 1 times 2 times 10 plus 1 over 6 minus, and then we have 1 times 10, or C times N, 1 times 10. That's 10 times 11 times 21 over 6 minus 10, and that's going to be 375. We're going to go on to area. Area of the rectangle is area is base times height. Now consider the triangle. A rectangle is 2 triangles. If you cut that there, you get 2 triangles. So the area of the triangle is half that of the rectangle. Area is 1/2 base times height. Now here's what we're going to be doing with calculus. We can approximate, we talked about this the very first day in this class, we can approximate the area under the curve by looking at rectangles. The rectangle that goes up that. And we can do more and more of these. So the area of an irregular curve or curve figure can be approximated by using a rectangle or triangle. We typically use rectangles, or many rectangles and triangles. This is an example of a lower sum because the rectangles go to the lower part of the curve. Over here is an approximation of an upper sum. Each rectangle is above the curve. So the highest point of the rectangle, from either side, the highest point is drawn. And so this one's an over approximation, this is an under approximation. This one's also called because we're looking at the right side of every curve, right side of every rectangle for the height, right side of the interval for the height of the rectangle. Right side approximation, left side approximation. Because for each interval, we get the height from the left side. Now, that looks really daunting. What we're going to do is find ways to use algebra with this concept in mind, having a bunch of these, in fact, an infinite number of rectangles to approximate it to give us the exact area under the curve. So inscribed rectangle is a rectangle lying inside the ith subregion of the curve. Circumscribed rectangle is a rectangle extending outside the ith subregion of the curve. So this is circumscribed, the previous was an inscribed. If f of mi is the height of the ith inscribed rectangle, and f of capital Mi is the height of the ith circumscribed rectangle, with this understanding we can define upper and lower sums. So our lower sum, little s sub n, is the sum as I goes from 1 to n of f of mi delta x. This gives us the area of the inscribed. And the circumscribed has a capital S because it extends beyond. I goes from 1 to n of f of mi delta x. So now the key to this is to be able to come up with enough intervals so these are the same value. Then we know we have the actual area under the curve. And I want to stress in each case, area is base times height. Well, this is the base, this is the height. This is the base here, this is the height for each of those rectangles. F of mi, either capital or lowercase, is the height. So let's get, we're going to bound the area of the shaded region by approximating the upper and lower sums using rectangles of width 1. Okay, so I have 2 colors here. For the upper sum, we'll use blue. So here's a width. Go up to the highest point there. We have that one. Go to the highest point there. The highest point here. It goes up there actually. And the highest point here. Okay. So this is 5. We have 5 times 1 from this part. Another 5 times 1. This is going to be 4.2, so 4.2 times 1. That's my approximation of the height, and this is going to be about 2.3. So the upper curve would be about 16, the upper approximation, 16.5. Now we'll do the lower approximation in orange, because I like orange. Lower sum. So we're going to go to the lowest point in each rectangle. And then we're down to 0. Okay, so we're going to have 4.2 times 1 plus 4.2 times 1 plus 2.3 times 1 plus 0 times 1. That one comes out to be 10.5. So we know that the area falls between 16.5 and 10.5. Let's do another one like that. The next one, we actually have the formula. Y equals the square root of 1 minus x squared. So it says use upper and lower sums to approximate the area of the region using the indicated number of subintervals of equal width. So we have 1, 2, 3, 4, 5. So 5, we're going to have the upper and lower. S5 is the upper, capital S. And there. Not going to be able to get it all on the same screen. I'll leave it like that, and we'll do a little s of 5 here so you can see it all together. Okay, now this is 0.2, 0.4, 0.6, 0.8, and 1, because our delta x is 0.2. Each interval is a 0.2 width. So for the first one, it's going to be, this height right here is 1. What's this height going to be? That's going to be 1 minus 0.2 squared, and that is square root of 1 minus 0.2 squared. That's 0.98. I think it's 0.96 actually. And then the next one is going to be right here, the square root of 1 minus 0.4 squared. That's 0.92, this says here. Please double check these values. Oh, it's square root, yes. So it is 0.98. Okay. And then this one is going to be the square root of 1 minus 0.6 squared, and that's 0.8. And then we have the square root of 1 minus 0.8 squared, that's 0.6. And of course this is 0. So for the upper sum, we take the highest of each of these intervals. So we have 1 times 0.2 plus 0.98 times 0.2 plus 0.92 times 0.2 plus 0.8 times 0.2 plus 0.6 times 0.2. And that is 0.86. That's the upper sum. That takes the higher one. For the lower one, so for the upper, we do that higher line in each case. Now for the lower sum, we're doing the lower line. Now it's going to be 0.98 times 0.2 plus 0.92 times 0.2 plus 0.8 times 0.2 plus 0.6 times 0.2 plus 0 times 0.2, and that would be 0.66. So quite a difference there. To have more accuracy, we should have more intervals. Now, when we get to it, we'll actually be able to get the exact value of this curve. And it'll be less work than this approximation. Okay, I'm going to go on to the next page, so pause if you need to pause. So as I talked about, having more and more intervals, you have more and more accuracy. So let f be continuous and non-negative on the interval from a to b. The limit as n goes to infinity of both the lower and upper sums exist and are equal to each other. That is, as n goes, the limit as n goes to infinity of s sub n, with the limit as n goes to infinity of I going from 1 to n of f of mi delta x. And it's key to point out here that delta x is b minus a over n. So you have infinitely small intervals. So if you have an infinite number of intervals, you're going to have the actual area. And that works out to be the same as the limit as n goes to infinity, I goes from 1 to n of f of capital mi delta x, which is the limit as n goes to infinity of s, capital S of n. So as you have an infinite number of intervals, and this is not an impossible thing, and that's what we're going to be doing. We're going to be doing this. And we'll do it the long way, just as we found the derivative the long way, then we'll do it the short way. And you'll spend the rest of your career doing things the short way. But I want you to get the understanding of what we're doing with these infinite sums. See, sums, infinite sums. We're adding things infinitely. Okay, and I know that that's probably one of the bigger stumbling blocks for people in calculus is this infinite sum thing as working through the algebra. Just understand it's a necessary thing to do, to understand. So definition of the area of a region in the plane. Let f be continuous and non-negative on the interval from a to b. The area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is, area is, the limit as n goes to infinity, of the sum I going from 1 to n of f of ci delta x. And ci is some value between either end of the interval we're talking about, where delta x is b minus a over n. And that brings us to example 5. It says, find a formula for the sum of n terms. Use the formula to find the limit as n goes to infinity. Okay. So what we have here is the limit as n goes to infinity. Now, in the sum, I is the index, so it doesn't affect the 16 over the n squared. So this is 16 over n squared, sum of I, as I goes from 1 to n. So the idea is to try to evaluate it with the I. That's what we're doing right now. And then we'll come up with a lot of algebra. So we will be going to algebra with this. And we saw this sum before. This is the limit as n goes to infinity. Now I can't take the n squared out of the limit part because it has the n there, and it's the limit as n goes to infinity. 16n over n squared times what? Now the sum as I goes from 1 to n of I is going to be n times n plus 1 over 2. We saw that. And that's going to be the limit as n goes to infinity of what? 16 over 2 times, and from here we have n squared plus n over n squared. Now I can pull the 16 over 2 out. That's 8. Maybe I shouldn't skip steps. Limit as n goes to infinity of 8 times n squared plus n over n squared. That's 8 times the limit as n goes to infinity of n squared plus n over n squared. That's 8 times the limit as n goes to infinity of n squared over n squared plus n over n squared. That's 8 times the limit as n goes to infinity of 1 plus 1 over n. That's 8 times the limit as n goes to infinity. Well, actually I could take the limit now. that becomes 1 plus 1 over infinity. 8 times 1 plus 0, so it's 8. So the area under the curve for this formula is 16I over n squared. It's going to be 8. And we're going to go on to the next page, our last page from this section. It's been a long section, but we're getting through it. So pause if you need to pause. And my blue pen's getting a little dry. It says use the limit process to find the area. Let's see if this pen's any better. Of the function and the x-axis, or between the graph of the function and the x-axis over the given interval. So y equals x squared plus 1 from 0 to 3. What we're talking about here is a curve like that from 0 to 3. We want this area. So our delta x is going to be 3 minus 0 over n, or 3 over n. And f of x equals x squared plus 1. So mi, any term for any interval, is going to be 3 over n times I. Or I is whichever interval we're on. So our sum s of n is going to be the sum I goes from 1 to n of f of mi delta x. That's going to be the sum as I goes from 1 to n of f of 3I over n times 3 over n. And if it just helps to see this, here's 0, here's 3 over n, here's 3 times 1 over n, here's 3 times, I should say this is 3 times 2 over n, 3 times 3 over n, and we get out there, here's 3 times I over n. Okay, so plugging this into our function, that's going to be 3I over n squared plus 1 times 3 over n. So I can pull this 3 over n out. We'd have, I didn't do the limit part, I'll do that at the end. 3 over n times the sum as I goes from 1 to n of what? 9I squared over n plus 1. 9I squared over n squared, there. So we have 3 over n times the sum I goes from 1 to n of 9 over n squared times I squared plus 1, the sum I goes from 1 to n of 1. So it's 3 over n times what? We have a 9 over n squared times the sum of I squared plus this sum, which is going to be 1 times n. So it's 3 over n times 9 over n squared times the sum for I squared is going to be n times n plus 1 times 2n plus 1 over 6 plus n. So it's 3 over n times, and the 9 and the 6 can be reduced a little bit. So this n times n plus 1 times 2n plus 1 works out to be, we have that 3 halves times 2n cubed plus 3n squared plus n over n cubed. So this part right here works out to be this right here. This is n squared down below. If I bring the 3 over n through, that's going to be 9 halves times 2n cubed plus 3n squared plus n over n cubed times 3 times n over n. Now the key to this is that if we take the limit as n goes to infinity of our s of n, we have the limit as n goes to infinity of this quantity, 9 halves times 2n cubed plus 3n squared plus n over n cubed plus 3. Taking this limit as n goes to infinity, what happens here? Well, all the terms with the power less than 3 are just going to go away. And we're left with 9 halves times 2 plus 0 plus 3. That's going to be 9 halves times 2 plus 3. 9 plus 3 is 12. That is our sum. Okay, so that's a lot of algebra we had to do there. I know the big leap I took, I just multiplying this out, you get this expression. You're free to use that. You don't have to multiply it out every time and reinvent the wheel. Okay, I have one more example from this section, so pause if you'd like to pause. It says use the limit process to find the area of the region between the graph of the function and the y-axis over the given y-interval. So f of y equals 3y. So in this case, we're looking at this function here. From 0 to 2. A little odd for us to see it that way. So our delta y is going to be 2 minus 0 over n, or 2 over n. So the mi is going to be 2 over n times I. So in this, you'd have 0, then you'd have 2 over n. Next one, 2 times 2 over n, 2 times 3 over n, 2 times I over n. So S of n is going to be the sum I goes from 1 to n of f of mi delta y. That's going to be the sum as I goes from 1 to n of f of 2i over n times 2 over n. That is what? 3 times 2i over n times 2 over n. 3 times 2 times 2 is 12i over n squared. I'm going to pull that 12 over n squared out. We have the sum I goes from 1 to n of I. That's 12 over n squared times I plus 1 over 2. No, sorry, n times n plus 1 over 2. That's n squared plus n over 2. So we have is 12 over 2 times n squared plus n over n squared. That's 6 times n squared plus n over n squared, which would be 6 times n squared over n plus n over n squared. Square down below. 6 times 1 plus 1 over n. So if we take the limit of s of n as n goes to infinity, we're going to have the limit as n goes to infinity of 6 times 1 plus 1 over n. That's going to be 6 times 1 plus 1 over infinity, which is 6 times 1 plus 0, 6 times 1, which is 6. You can kind of see this is the case because if you plug it in, 2 times 3 is 6. 1/2 base times height. That's 1/2. 2 times 6 is going to be 1/2 of 12, which is 6. So, makes sense. Okay, well that'll do it for 4.2 areas. A few more problems, a few more chapters or sections like this, but it'll get better, trust me. Hope this is not too intimidating. I know it's new. Plugging in these formulas, plugging in these algebra formulas, but we can do it. I believe in you. Okay, send me your questions. Thank you.